Hello and welcome back to another video. In this video, we're going to be taking a look at a CSTR example problem. Now, a CSTR, that stands for Continuously Stirred Tank Reactor, and you can see sort of what this looks like here with this picture on the right. Essentially what we have here is we have a reactor, and this object here is a stirrer, so it's stirring the contents coming into the reactor. And we also have this sleeve of coolant water on the outside. So this blue sleeve here is coolant water because this example problem here, we have an exothermic reaction. So we want to keep this reaction as cool as possible. So here on the left here, we're given this problem here, and it says to illustrate how the CSTR, again, the continuously stirred tank reactor, can exhibit a nonlinear dynamic behavior. So essentially, the behavior doesn't move forward in a straight positive line. So that's what nonlinear means. We simulate the effect of a step change in the coolant temperature Tc, so the coolant jacket here, in a positive and negative directions. Table 2.3, so this table down here shows the parameters and nominal operating condition of the CSTR based on equations 266 and 268 for the exothermic irreversible first order reaction A to B. So we have that written here in our picture. The two state variables of the ordinary differential equations are the concentration of the contents inside the tank, so Ca, and the reactor temperature T. The manipulated variable is the jacket water temperature Tc. So essentially, we'll go ahead and finish reading here. It says the two cases are simulated, one based on increased cooling by temperature by changing Tc from 300 Kelvin to 290 Kelvin, so a drop in the coolant temperature, and one reducing the cooling rate by increasing the cooling temperature from 300 Kelvin to 305 Kelvin. So essentially what we need to solve for here in our derivations for this problem is the change of the concentration of the contents here inside the reactor with respect to time, and also the change of the reactor temperature T with respect to time. So what I'm going to do here next is go ahead and write this up on our whiteboard. And what we'll need to do here is, since we're not given what these parameters are here, we can use a little bit of common sense to determine the parameters here, and then go ahead and derive our expressions, like I said, for the change of the concentration of the contents inside the tank, and then the change of temperature of the contents inside the tank. So once we derive that, we'll actually be able to go into Python and solve the problem and go ahead and plot it to sort of set up a simulation to see what this process would look like.
All right, so I've gone ahead and drawn a picture here of our example problem and gone ahead and written out our parameter and the different values that are associated with our parameters for this problem. Now, before I go forward here, I think I actually forgot to mention a very important thing about this problem. And since it's a CSTR, a continuously stirred tank reactor, this means that the concentration inside the tank here equals the concentration that will be leaving the tank, so the stream going out of the tank. The concentration going into the tank will obviously be different. Since the contents in here are stirred and then released outside, the contents going in and the concentration of the contents in here stirred will be different. So if we go ahead and take a look at our parameters here, we aren't necessarily given what these parameters mean in terms of this problem. So if you look here, just going down the list here at our first parameter here, this Q parameter. Well, we know that Q usually stands for flow, and we're just given one Q value here of 100 liters per minute. So we can assume that the flow going into the tank is the same as the flow going out of the tank. So the next parameter here is the CAI. So here we might first assume that, well, this might be the concentration of A, so our A substance here, initial. However, if we look down at the bottom here, we have this CA naught, and this signifies that this will be the initial condition for the concentration of A. So what this CAI means is actually the concentration of A coming into the tank. So just like I said before, since the concentration of the contents going in are different from what's inside, this is actually the concentration of A going into the tank. Next on our list here is this TI. So again, we might think that this is the initial temperature. However, this is the temperature for the contents going into the tank. Next here is our volume. And we notice here that our volume here is just one value, 100 liters. So this tells us that we have a constant volume reactor. Our next value here is this density here. And we have this as 100 grams per, or excuse me, 1,000 grams per liter. So this tells us that we're working with water in this example because that's the density of water. Next here is this C parameter. Now this C parameter is what's known as the heat capacity. Now we're only given one value for this C parameter, so we can assume that the C parameter is the same here for the contents going in, the contents stirred, and the contents leaving the reactor. Next here is this negative delta HR, and what this is this is the enthalpy of reaction for this reaction. And since this reaction is exothermic, we actually have this negative here, and the value for it is 5 times 10 to the 4th joules per mole. So this would make sense with it being a negative value since this is exothermic and heat is being released. These next two values here, this E divided by R and this K naught, these are parameters that are associated with what is known as the Arrhenius equation. Now the Arrhenius equation is written as follows. So we will have K equals K naught times the exponential of E divided by R divided by temperature. And this E divided by R here is actually negative. So what this shows us is how the reaction rate here will depend on either an increase in temperature or a decrease in temperature. So from here we can actually write down, before we go any further, an expression for our rate here. So we can say our RA here for our rate is equal to Rk, which is the Arrhenius constant for this equation. So Rk times the concentration of A. So K times Ca. Okay? So this ER value here is what is known as the activation energy. So most of the time when you see this equation written, this term here is denoted as EA. However, it is E divided by R. So continuing down our list here, this UA here is what is known as the heat transfer between our reactor here and the coolant water that's flowing on the outside of our reactor. So this is what's known as the heat transfer times the area of our reactor here. So we can actually go ahead and write an expression for this. So we can say the heat transferred between reactor and cooling, or we'll just put coolant. This is equal to UV, so UA, our parameter down here. So the heat transfer times the area, and this will be multiplied by the difference in temperature here. So the temperature of our reactor here minus the temperature of our coolant here. Okay, so we have these two equations here, or expressions here, I should say. So I have 1 and 2 here that we can go ahead and draw from our parameters. And then continuing down our list here, we have these last 3 initial conditions here. So our TC naught, our CA naught, and our T naught. So this will stand for the initial temperature of our coolant water, or what is flowing around our reactor here. We will have the concentration of A naught, so the initial concentration, and we will have the initial temperature for our reactor. So now that we've gone through here and given a meaning to each of our parameters, now we can shift our focus back to what we are solving for in the first place. So we want to solve for the change of the concentration of A over time. So we want to derive a differential equation for this expression here, and we also want to find out what is the change of our reactant temperature, so the temperature of our contents in here, with respect to time. So now we'll go ahead and take a look here and see how we can derive expressions that would make sense for our two differential equations here. All right, so if we go ahead and look here at our first differential equation, so the change of the concentration of A with respect to time. Anytime we're faced with a problem like this here, so we're looking for the change in concentration of what we're working with, we always want to go back to the basics. So what is going in, so rate of accumulation, what is going in minus what is going out, and then minus whatever is consumed in the situation that your process is going through. In this case, we have a continuously stirred tank reactor. So if we look at what is going in minus what is going out, well, we know that we have the same flow rate for what is going in and what is going out. However, we have a different concentration of A going in and concentration of A going out. So since we have the same flow rate, we can go ahead and just multiply this by our concentration of A going in minus our concentration of A. And here our concentration of A, it's important to remember that it's the same for what is in this tank since it's continuously stirred and what is going out. So this gives us the of what is going in minus what is going out. Now, if we want to look at what is consumed in this problem, well, we have our reaction equation here. So this will actually give us the amount of what is consumed for our situation here. So we want to subtract here, since we're subtracting what is consumed, this K here, our Arrhenius constant for our Arrhenius equation, times the concentration of A. Okay, so this will give us our rate of accumulation here, which will allow us to solve for the change of the concentration of A with respect to time. Now this next one here, this change of the temperature of our contents with respect to time, is a little bit more tricky. So what we can do here first is just look at our left-hand side here. What terms do we have here to describe the contents of what we're working with, since we're looking at the change of the temperature of our contents with respect to time? Well, if we look over here, we have these three parameters here. So we have the volume here, which again is constant. We have the density of our contents, and we have the heat capacity. Well, we actually notice something cool here. If we look at the volume and the density here, well, we know that this will give us mass if we look at the generic equation, but we can actually, if we just want to go back to units here, if we multiply these, we will end up with grams. So that will tell us that we will get mass here. So if we multiply these here on our left-hand side, I know it's hard to see, I don't have much room here, but if I multiply volume times the density here, this will give us the mass of what we are changing in temperature here. And then we have to take into account the heat capacity here, so C, so I have to multiply that by C here. I know this is probably really hard to see over here, but this is volume times density times heat capacity times the change in temperature of our contents with respect to time. Okay, so now we can go ahead and try to set up an equation here for our right-hand side, or an expression for our right-hand side. And what we'll want to look at here is the change in internal energy of our system. And the first thing that we'll notice here is we have a different temperature here of what is going in minus, or not minus, but we have a different temperature here of what is going in and a different temperature for the contents going out. So we know we have some change in enthalpy here. So I'm just go ahead and write just a dummy term here, Hn minus H out. So this will give us our change in enthalpy for our system, so H in minus H out. And the other term that we have here for either change in internal enthalpy, or if you want to think of it as a heating term, we have this expression here that we have, so UA times the temperature of our contents minus the temperature of our coolant. And if you remember, this is just the heat transferred between our reactor and our coolant. So because this is a loss in heat, we will want to subtract this term here. So we'll subtract UA times the temperature of our contents times the temperature of our coolant, okay? So we have an expression here. However, what we can do here is we can actually take a look at this term here and write it out so that it makes sense for the parameters that we have here. So I'll go ahead and erase this, and we can sort of expand this out to include the parameters that we have. So go ahead and erase this here. Okay. So I'll go ahead and keep the same left-hand side here. So we'll have the volume times our density, which will give us our mass, times the heat capacity, and then we'll have our change in the temperature of our contents with respect to time. And here, if we, right off the bat, we can look at our change in enthalpy term here, our H in minus H out. And if you remember what I said here, we have a different temperature of our contents going in minus, or a different temperature for our contents going in, and a different temperature for our contents going out of our tank. So we know we'll have a change there. So we'll have our change here, so T in minus T out, and we know that our T out is the same as the temperature of our contents in the reactor, since it's a continuously stirred reactor. And let's take a look here at what makes sense for what we'll have to multiply this change in temperature term for here. Well, we'll obviously have to multiply it by our heat capacity here, since it's the same for both of our temperatures. We will have this on the outside. And also what we'll want to take a look at here is we have this volumetric flow rate here, Q, and we have our density here. And if we take a look at the units here, so I'll go ahead and write these down. So I have Q times the density. And if we take a look at our units here, we have liters per minute for our volumetric flow rate. We have grams per liter for our density, and our heat capacity here. If we look at our units, they will actually work out. So we have this term here. And from here, what we have is we need to take into account this reaction that's occurring here for the change in enthalpy. So if we go ahead and look here, we have, we can look at the amount of what is reacting here. So if we have the volume times our K, so our heating is constant, times our concentration of A, so this will give us the amount of our reaction that's occurring, okay? So we'll have this here, and this will have to be multiplied by the change in enthalpy here, so our delta HR of reaction here for our reaction, since there is being heat released to the system. And we'll have to go ahead and add that on. So this is actually negative delta HR, and these two, this negative delta HR and these two terms are multiplied here. I know this is, I'm running out of room here, so let's go ahead and read off here. We have added on our amount of what is reacted, so our volume times our K, our heating is constant, times our concentration of A, and then multiplied by the change in enthalpy for our reaction here, which will essentially, this is releasing heat, so this is a negative term here. And lastly here, we will still have our minus our heat transfer between our reactor and our coolant. So UA times T minus TC. So I'm running out of room here, but this term is subtracted on the end here. So actually what we can do here is we can go ahead and, since we want to isolate the change in temperature of our contents with respect to time, we'll go ahead and divide over our volume times density times heat capacity for all these terms here, and this will allow us to isolate here our change in temperature with respect to time. So go ahead and erase this, and hopefully I have enough room. All right, so we'll have our change in temperature of the contents with respect to time, and dividing across volume times our density times our heat capacity, we will be left with, well, our all right, so we have our change of the temperature of the contents with respect to time, and dividing across our volume times the density times the heat capacity, we will be left with just Q over V times our change in temperature, so Tn minus T, okay? And then we will have to add, and then looking at our change in enthalpy for our reaction here, we will have our negative delta HR multiplied by, and since we're dividing by volume here, our volume for our amount of what is reacted here will actually cancel out, so we'll just be left with K times Ca, and then over density times our heat capacity C. And our last term here, our term that takes into account the heat transfer between our reactant and coolant, we will actually be ended up with the entire term divided by volume times density times heat capacity. So we'll have our UA times T over the temperature of our contents minus TC, so the temperature of our coolant, divided by our volume times our density times our heat capacity. Okay? So we have now gone ahead and isolated here our change in temperature of our contents with respect to time. So these here are actually our two equations that will allow us to solve for what we're looking for, the change in concentration of A with respect to time, and also the change of temperature of our contents with respect to time. Now, just to mention this bottom differential equation here, we basically, believe it or not, just set up an expression for an energy balance here without fully writing out. If we fully wrote it out, we'd have a bunch of zero terms because, well, we don't have a change in kinetic energy here since our flow rate is the same, and we're not given any other information about necessarily having a change in kinetic energy. And if we look at potential energy here, we're not told that we have a different fluid level height or a different inlet line here than the height of the discharge line here or anything like that. So if we did a full-blown energy balance equation here, which we could have done, we would have a bunch of zero terms. So essentially what we did here is this energy balance, looking at the internal energy here of our system. So if we take these two equations here, we can actually go into Python and use the solve IVP solver, which will allow us to solve our initial value ordinary differential equation problem. And if we supply the right-hand side of our two equations here, it will allow us to solve for what we're looking for, and then we'll go ahead and plot that to see what the problem asks us to do. So the change in temperature here, and see how that fluctuates on a graph to set up a simulation to see how our system would respond to it. So that's what we're going to go ahead and do next.